All right, I think we can get started. Good evening, everyone. Welcome to the second simulation webinar today. I am Yashima and I will be moderating the session. Today in this session, you will learn about how to populate the construction details for solar and thermal calculations in Design Builder. You will also get to see examples from real projects, which will help you understand how to use results from your analysis to choose the right kind of envelope for your building. Before we begin, I would like to acknowledge the support of the Department of Science and Technology and all our supporters and affiliates. Today, we have with us Mansi Parikh and PC Thomas. Mansi is a senior sustainability consultant and has key qualifications in the field of passive design, low energy cooling and HVAC systems, lighting and daylighting design. She has worked on various projects with goals leading to net zero energy, water, and waste. We also have with us PC Thomas. PC is the founding director of Team Catalyst and also an adjunct professor at the University of Sydney. He specializes in integrated building design using simulation tools to assist in the design and delivery of sustainable buildings, in particular in predicting the performance of mechanical services. He has a master's degree in mechanical engineering, 30 years of consulting, research, and teaching experience in sustainable buildings, building energy simulation, energy auditing, energy efficiency in buildings, and solar energy. Hi, PC, and hi, Mansi.
Hello, hi, Ashwin.
Hi. With that, I'll pass it on to you, Mansi, and then we'll pass it on to PC after that. Thank you so much for joining us today.
Thank you. I'll start sharing my screen. Okay. Can you see my screen?
Yep, we can see.
All right, perfect. So I'll start. So hello, everyone. In today's webinar, we are going to discuss about shading design and parameters for envelope selection. So in this presentation, this is based on a particular project which I worked on for an upcoming net zero campus for Ashoka University. This university is based out of Hisar, Haryana. The campus is going to be net zero in terms of energy, in terms of water. They have aspirations, and the climate here is similar to Delhi, which has both extremes, summers as well as winters. So when we start looking into, when we start looking into shading design or envelope selection, the first step we take for shading and envelope design, and envelope selection is to do irradiation studies on a particular facade to understand the requirement. So this gives us an idea for if the shading or insulation is required to control, heat gains through direct solar irradiation, which is falling on the windows of your facade or directly falling on the walls. So in this image shows the irradiation on a facade in north, south, west, and east. And this varies from the range of 200 to 1200 kWh per square meter per year. Okay, so as you can see on your screen here, the ones which are blue, depicts the lesser irradiation, and the ones which are red shows the higher or the maximum amount of irradiation. This again is annual numbers. So I have a quick question for you guys. Yashima, can we have a question on the screen?
Yeah. So the first question for today is this: to control solar gains, which facade should be provided with shading? And the options are north, south, east, and the fourth option is south, east, and west. So I would request all of you to put in your answers, and we will discuss once we have enough answers from the audience.
Shading and envelope design is a very crucial part for when we are designing for a net zero building or a passive design aspect of it. So this is the first study which we do generally. I think these studies can be done in Design Builder as well, PC. Correct me, right?
Yes, you can. Thanks.
All right, we have a lot of responses coming in. I will now end the poll so that we can look at the results. And Mansi, here are the results.
Wow. So most people are right here. And the answer is option D, which is south, east, and west. I'll tell you why. So basically, as you can see that, maximum irradiation is falling in these facades. You can see bright red on south facade. You can see orangish on east facade, and in the west facade is quite yellow. So around 850 to 900 kWh per square meter per year. So what we did was, we started providing, we designed shading for windows in west, south, and east facade. And further, to reduce envelope heat gains through walls, we started looking into options for insulation for these walls as well. Moving forward, the next step for after, looking into the irradiation studies, the next step is looking into the shading design. So how do you design shading? And, the important part is which months do you shade a particular window? So for this particular example, we are looking into, I'll tell you how we started designing for a window in a south direction. So now we have an interesting question which is going to come up. So Yashima, can we project the question?
Yeah. So the next question is, why should shading be provided on the southern facade? And we have three options. One is glare control, one is solar control, and the third option is solar and glare control.
We generally tend to feel, you might have observed that, when we are sitting right next to the window, generally people feel at times thermal discomfort and comfort based on the season which they are sitting right next to the windows. So you might feel uncomfortable after 5 p.m. or say you feel very uncomfortable during summer months. So that has to do with these both parameters, either of them. So.
Right. So we have a lot of responses coming in. I will now end this poll so that we can look at the results. Mansi, here you go.
Oh, wow. So great. So we have maximum responders saying that, the option here should be glare and the solar control both. Correct. That's the right answer. So shading should be provided for the southern facade for the glare as well as solar control. So as you can see, that is shading is generally provided for solar control, that is to reduce the heat gains and to reduce the glare probability in a particular space. Generally, lower angle sun, like generally in the winter timing and monsoon sun can cause glare probabilities in a particular space. So a person, as I said earlier, that person sitting next to a window might experience glare probability during the lower angle sun. So you might also have faced that, post 5 p.m. you feel glare. During the daytime, your windows will be well shaded, okay, with less amount of shading. However, when the angle of the sun is lower, it is difficult to control the glare. So on the image in the left shows that solar control. So these are the angles which were provided to reduce the solar control in a particular space. We tried to provide both solar and the glare control from 9 a.m. to 2 p.m. So that is for solar control, and the glare probability, we provided shading to reduce the glare probability post 4 p.m. also in the winter months. So as you can see, we have shaded for essentially two parameters, that is for solar and the glare control. And as you can see that, this was the window size, right? So what we did was we divided the window into two parts. That is, the top pane was 0.6 meter and the bottom pane, we call it view pane, that is for 2 meter high. And then we provided separate shading for both of these windows as per the VSA required here. And then also what we did was provide a lighting shelf here. This is called the light shelf, where you are extending this into the inner side of a particular window to reduce the probability of a glare in a particular space. So these are certain measures which can be taken for glare controls. What generally offices does in terms of reducing glare is they increase the aisle space right from the window. We generally keep 1.5 meter distance from the window to the first table. or they increase the partition heights. So there are certain other measures which one can take to reduce the glare probability on a particular workstation. So, the next step after the shading design is to understand. So shading, again, like shading an envelope or say insulation would have an impact on your cooling loads. So in reducing your peak cooling loads or annual cooling loads. The image on left shows window shading options for a south facade. The options are single glazing options with and without shading. And the last, so there are three options. The first case is no shading with only AAC wall. The second case is shading with AAC wall, and the third case is shading plus 25 mm of insulation. Okay, and the graph on the right depicts the percentage reduction in peak cooling load, which is very crucial in designing for HVAC right sizing, system sizing. And the lower graph shows reduction in annual cooling energy. This is cooling, peak cooling load based on which we generally size our systems, and the bottom one is reduction in annual cooling energy. So just for a context, I would like to say that cooling energy in a particular building accounts for almost 50% of total energy consumption. For example, if an EPI of an office building is say roughly around 60 kWh per square meter per year, then almost 30 kWh per square meter per year would go into cooling. So selection of envelope also plays an important role. May it be your insulation provision or may it be your shading plays an important role in your HVAC systems and your cooling energy consumption. So all of these are interrelated. So, okay. So we have one more question coming up here. Yashima, can we project that on the screen?
Yeah. So the next question is, which is the most energy efficient case as per the graphs you see on the screen? And the options are case 1, 2, and 3.
So I would like to remind that case 1 here is with no shading, no insulation. Case 2 is shading and wall. So only shading, and case 3 is shading plus insulation on the wall.
All right, we have a lot of responses. Mansi, I will now end the poll. Yeah, here are the results.
Interesting. And most people has again given the right answer, which is case 3. So case 3 is most energy efficient case, so that helps. So option 3 here, which has insulation as well as, shading, works the best in terms of reducing the peak cooling demand or peak cooling load we call, and then annual cooling energy. So we selected this particular option. So in this particular set, in the education building here, we selected the combination of both shading as well as insulation to take that forward. Also, we did a similar sort of study for a DGU. This is all for a single glazing unit. The same studies can be done for double glazing unit to arrive at a correct result, because all of these measures individually would add cost to the overall design. So these sort of studies helps us to understand and to pick the correct measures. Now, this is also one way to look at the shading benefit analysis and the results. The image on the top shows irradiation falling on the facade without shading. So this is the option without shading. And the one on the bottom shows the vertical fins. So this is with shading. And by providing the shading, average irradiation on the facade could be reduced by 24%. Here, as you can see, the average irradiation falling on the facade was 140. However, when we start reducing it and when we averaged it out, it was roughly around 105. So this is also one way of looking into the irradiation studies. So the next so once you decide that, we want to start looking into shading as well as insulation, the next step for us to understand how much insulation should we provide on say, as we decided from the irradiation studies, right? We have to provide insulation from in south, west, and east wall, but how much? What should be the thickness of the insulation should be provided? So these is the wall sensitivity studies which we did for various facades. So on this particular graph, what you can see is wall sensitivity studies for south facade, south facing walls. So the x-axis shows the U values from 2.4 to 0.2 watt per meter square per Kelvin, and on the y-axis shows annual cooling load. So just for reference here, that you would require, so typical brick wall would have U value of 2.2. However, to achieve the U value of 0.2 watt per square meter per Kelvin, you would require 125 of XPS insulation. So there is again addition of cost here. So this sort of studies helps. So now we have a question coming up. Yashima, can you project the question, please?
Yeah. So the question is, as per the graphs, which wall assembly proves to be the most energy efficient for the south facade? And for the 4 options, we have 4 U values that we have been discussing. The first one is 2.2 watt per square meter Kelvin. The second option is 1. The third option is 0.4. And the last option, the fourth option, is 0.2 watt per square meter Kelvin.
Okay, so while this question is running, I would like to say to all the teams that the first thing when you are selecting a particular wall assembly, this is very essential. This wall sensitivity studies would help you. The next step for you is you can look into energy conservation building code. I am not sure how many of you are aware of it, but however, there are area specific, so location specific U values are mentioned in energy conservation building code, and there are a lot of other guidelines which one can refer to, and definitely you could refer to SLMs to look into these information.
All right. I will now end the poll, Mansi. Yeah, here are the results.
Interesting. So some of you had said that U value of 2.2 is the most efficient one, and most of you had said that U value of 0.2 watt per square meter per Kelvin is most efficient one. The answer is 0.2. Okay, I think the way you have to read the graph is that, these are U values from 2.4 to 2.2, and these are annual cooling loads. So as you can see, for 2.2, you have annual cooling load of 105 kWh per meter square. When you look at 0.2, it is roughly around 75. So there is a drastic reduction here. However, the interesting thing to observe in this particular graph is that there is hardly, when we look into 2 cases, okay, so 0.4 and 0.2, the reduction in peak, so annual cooling load was less than 0.5%. So this is rough. This is going to be this is 75, this is 80. So for the, 0.2, you had 75 annual cooling load of 75, and when you look into 0.4, that goes up to 76. Okay, so there was no much 76 or 77. So there was no much reduction beyond 0.4 of U value. Okay, so so what we did was 0.4 U value. I would explain why. So as I told you, right, typical wall would require 50 insulation to achieve U value of 0.4 here. Okay, and if you want to achieve, say, 0.2 U value, you would roughly require 100 or 110 of insulation. Adding insulation would add cost. So this is, so this would so adding 100 insulation, this would almost increase the cost of insulation to 4 times as compared to as compared to U value of 0.4 to achieve the U value of 0.4 with a very minimal energy saving. So we selected U value of 0.4 in this particular case. So there are various parameters which we start looking into. So it is, we have to weigh two parameters here. So reduction in, say, your energy efficiency, and the second part which goes along with is the cost of it. So next step, what we did here was we started looking into various assemblies options here. As you can see that, we can achieve 0.4 U value, but there can be different options for the same, right? So the option one here was brick wall with we had to provide insulation. So what we did was provide 60 of XPS. The second case was AAC block with XPS. So that would require roughly around 40 of XPS, because AAC wall has U values of 0.7 itself. Okay, so that would require less amount of insulation. The third case here, we looked into if there are concrete blocks, then there was again 60 of insulation was required. And the fourth case which we considered was hollow concrete blocks, that again required 50 of insulation. So there are various ways to achieve that U value of 0.4. So what we did was started looking into 4 various ways, and then we also simulated all of these cases to understand which is performing better. Now the next step was providing insulation. Where should you provide insulation? Say if there is a brick wall, where should you provide insulation? On the outer side or on inner side? So we did a very quick study to understand. So this is again for a naturally ventilated corridor. What we did was to understand where the location should be on the of the insulation. So it can be provided here, as you can see, okay, right on the inner side of or the wall, or this can be placed here on the outer side. So what we did was we studied for naturally ventilated corridors. This was found that insulation was provided on the outer side. Where this is where the insulation is provided on the outer side, there was minimal difference in the resultant temperatures. So in this particular graph, the way you have to read it is, this is for a typical summer week. The line on the most top is your external temperature, outdoor temperature. The line below it is the ground, that is your dry bulb temperature. The green line depicts the resultant temperature, and the red is the internal wall temperatures. So as you can see, it was seen that walls were more, there was no much, when we provided the insulation on the outer side, there was no much change in terms of wall temperature and resultant temperature across the day. The variation was minimal. So the next step for us to understand, so for a naturally ventilated corridors or naturally ventilated spaces, where should you, what should be the percentage of opening? Generally, the way we think is that, when you start providing windows, you would believe so that there is going to be inverse flow of air, but that's not always the case. Window has to be designed. There are a lot of various factors which come into play when you are designing for windows. That could be your air pressure, there would be your direction of the window, location of the window, wind speed which is going to come in, if it is cross ventilated, or if there is only ventilation on single side. So all of those factors weigh in, and what is the percentage of opening, all of those factors weigh in when we are designing for a naturally ventilated space. So here in this particular chart, what we did was we studied 2 cases. So in this particular graph, the x-axis shows percentage of opening of windows, and y-axis shows hours comfortable. This is again for a naturally ventilated spaces, hours comfortable across the year. So what we are calling comfortable hours are where the temperatures or resultant temperatures, or what we feel is less than 28 degrees. Maximum temperatures are maximum hours are less than 28 degrees. So and these are the 2 cases which we have here. On the top, case 1 has windows only on one side, as you can see, and in the case 2 we have windows on both sides. So basically we have a natural ventilation or cross ventilation happening here. So Yashima, we have a question coming up. Can you project that?
Yes. All right. So the next question is, which case performs better with respect to thermal comfort? And the two options are case 1 and case 2.
So, so what happens, what I have seen in projects is that, we start designing as an architect, we would start designing windows and we would seem that, it can be opened. But there are, again, for what I've seen so far is for the occupants to keep that open, there are various other parameters which come into play. Is there a mosquito mesh or not provided? That would play in an account. What percentage of that window is operable? So say if you're sliding window, you could operate it at 50-50. If you have the fully openable windows, then you will roughly get around 90 to 95% of clear opening. And that clear opening is very critical in sizing for natural ventilation for your optimal window sizing. So,
yep. Okay, I'll now close the poll, Mansi, and we've got the results in. Here are the results.
Okay, maximum. So, okay, here again, most of you are correct. The answer is case 2, because you have to, because this is the better case, because you are providing cross ventilation here. We get maximum percentage of opening. So that was again a better working case. So what we did here was we provided these sort of setup, these windows to improve the natural ventilation and to improve the cross ventilation in the space. And what we saw was that we could provide opening ratio. So how much windows can be operable to be 0.5. So sliding windows would work here, because beyond 0.5 there was very much very less decrease would you observed in this very less increase in terms of percentage comfortable air. So it is stagnant at 60. At 0.5% operable window ratio, it's stagnant. Post that, there is very minimal change. So as you can see, what we did was we introduced this particular windows of 0.6 meters, and resultant temperatures across the years across the year could be increased up to 60% in this particular case. So what happens is there is a possibility. So what we did here in this particular building was, we had various WWR, window to wall area ratio, for various floors, considering the courtyards, considering the amount of daylighting required in the space. So this is a possibility, and this is what we proposed as to the board. And yeah, this is what we did. Thank you.
All right, thanks, Mansi. So we are actually running a bit short on time, so I'll just pass it on quickly to PC, and then we'll take questions in the end.
Sure.
Yeah, all right. Thanks, Mansi. PC, over to you.
Hi.
Hi.
Okay, yeah. Can share my screen when you're ready.
Yes.
Okay, so we'll do exactly what is in the topic today. Mansi's lecture was very interesting, and you guys should go back and listen to it carefully. There's a lot of stuff there that's very, very useful, which we can do with Design Builder as well. So what I did is I think to show you how constructions work, we're going to look at just an ideal flow plate, because it's easier to work out some of those things. What I've done is that this typical floor is this middle floor. And what I've got here is a octagonal shaped building. You will see that it has got glazing everywhere, except this north bit here and this south bit here. These two bits are opaque, and all the other external walls have got some windows. We'll come to windows in a minute, right? Now, what I've done also is just to make sure that we are only looking at loads for that typical floor. I have cloned a couple of floors, one on the top, one on the bottom. Both have got adiabatic properties. That means that there's no heat exchange from above or below. So we're only going to be looking at the heat gains on that particular floor. Okay. Now, to set constructions, if you go and look at the help file in Design Builder, and you can just Google Design Builder help version 7, and you'll get the help file. I've searched for this thing called combined construction. I think we might have discussed it in the previous webinar. If not, the reason is that there is a very useful diagram on this page, which actually explains how Design Builder works. So once you finish the geometry, Design Builder is smart enough to go and check which is an external wall, which is an internal wall, which is a ground floor, which is an internal floor, which is an external floor, and it gives you all these names. Excuse me. So we just need to fill in the constructions in this screen, and then it goes and applies them across the building. Now, obviously, if you have a different construction in one particular zone or one particular wall, you can go to that particular wall and change things. But what I'm going to do is at the building level, we are going to apply something. So the first thing I thought, and I built this while Mansi was talking, is I've created this thing called an uninsulated aerated concrete cement wall with plaster. And if we examine that, what I've done is I put 3 layers. So it's just plaster, cement mortar, 13 millimeters thick. Then I've got aerated concrete block. I can make that 200.2 meters. And then I've got another layer of plaster here. Okay, and all of these materials you can select from within Design. So I've gone to this folder. You can see there are many folders, lots of materials here. So I've gone to the folder.
PC,
Yep.
your voice is becoming a little unclear at certain places.
Okay, thank you for telling me that. I'll try and hold the mic up to my
this is
face.
better.
Is that better?
Yes.
Yeah.
Yes, this is good.
Okay.
Yeah, thanks.
No worries. Thank you for that. So here's my aerated concrete block. And you can see on the right-hand side, those properties. You can even examine those properties. And if you don't like those properties, you can make your own. Okay, but just remember, when you pick something that's in the library that will be a locked library data, you just need to make a copy of it, change the name, and put your own. But for the present, we're going to use this. Okay. So these 3 layers, when you're looking at it, will be cement plaster, aerated concrete block, plaster again, outer surface, inner surface. And then if you ask it to do the calculation, it will work out for you what is the U value. Okay. So what we can do is with that U value, which is about 0.945 or 0.95, you can run your energy simulation. You can get some energy numbers. Okay. So let's do that. I've chosen Delhi here as the location. So to do that, I went to the top there, went to the location tab, and then I selected here New Delhi, and I think there's 2 New Delhis. There's Parliament, Safdarjung, but you can choose either. I've chosen one. And this is the simulation weather file that it has loaded automatically. There are some design temperatures that are going to be used to calculate sizing of air conditioning systems, cooling load peak cooling load that Mansi was talking about. And there's a winter design temperature to size heating system. So they're all there once you select the location. Okay. I also don't have any detailed air conditioning system because I'm only interested in the facades at this point. And one other thing I might do is I might just change, I will go back and look at openings in some detail. But what I can do is I'll just change I'll make a copy, that's the easiest way. I'll change the window to wall ratio not to be 80%, but something less. Let me say 60%. Okay. And in there, I'll change this to 60%. For the present, I will leave that there. And then I'll apply that. So I've used a template with 60% glazing. And when I do that, you can see here the dark gray areas have now increased. Okay. So my model has got a strip window on all facades, 60% window to wall ratio. And we'll talk about the performance of the windows after we finished with the performance of the construction. So let me just do a quick run. Here we go. So from 1st Jan to 31st December, make a run. And it will generate for me the annual heating and cooling energy required. Now, I haven't checked other things. So when you are working out heating and cooling loads, it needs to know how many people there are, what is your lighting system, what is your lighting system? Oh, hang on. What's going on here? I got a new version of everything, so hopefully it's all. Okay, it's doing that. Yeah, should work. Yeah, I was saying that it will work out. What's going on? Sorry. That's very embarrassing. That's all okay. Okay, let's try this instead. I think I've got something where it's taking over and running a plugin, which it shouldn't be doing. But we'll see in a second. No, it won't do that. Let me pull another. Let me pull another file, which I know runs. Well, okay, I'll pull another model, which hopefully will run. We'll test it out and we'll see how it goes. But essentially then what you can do is you can run an energy simulation, you can run a peak cooling load simulation. All of those can be done in one or two runs. And then you can change your construction and redo that again. Then you can add shading devices and redo that again. So let me remove my air conditioning system. So no detailed air conditioning, just a simple one. And first, let's make sure that it runs. Otherwise, I'll have to uninstall my plugin. Yeah. So before it runs, it's first working out the peak cooling loads. Then it populates the peak cooling loads in each zone, and then it runs the energy numbers. So right now it's running the energy numbers. It's doing it for Sydney. Let it do it. And then I'll show you how I look at the energy numbers. We'll change the construction, redo it. And then I'll show you how to look at the peak cooling loads. So those 4 things we can do by just doing constructions. Then we'll have a look at how we can change window performance. So right now, it's running through the whole 1-year simulation. And as I said, let me do that. There are many things that go into that. So you're making some assumptions about constructions, the way the building is occupied, what kind of energy you're using for lighting, what kind of energy you're getting from equipment in your spaces, and how the building is using all of that. And then, of course, the weather files. So we're almost there. Okay, so it's finished the energy simulation. I don't want it to load it back into Design Builder because I already know it has written the results for me. So I'll go to the files and I'll go to the Energy Plus folder, which is where all the results are. And if you look at my timestamp is 11:14 p.m. Of course, it's about 5:30, 5:45. And these are the results that came out. So the energy numbers are available in this file here, the HTML file. It tells me that I've done a full year's run. It is for Sydney. I can change that. But really speaking, you're really interested in these 2 numbers here, district cooling, district heating. So that's the amount of cooling energy you need, thermal energy that you need to keep the space within the thermostat constraints. And this is what you need for heating during some preset times. And since this is an office building, I most likely would have set it to be working between 7 o'clock and 6 o'clock, Monday to Friday. Okay. Now, if you change the construction and you rerun it, you will see the change in energy use. Okay. So the way to do that is to, go out and have a look at what's in your wall construction and change it. Okay. So let's do one thing. Let's just note what it is, and then we'll work it out. So here I have got the cooling number is 74,726 kilowatt hours, and the heating number is 7,139 kilowatt hours. Okay. Now, the reason I said I look at it is because I can see that I've got a fairly well-insulated wall. Okay, I've got an insulation already as part of the wall. So if I remove that insulation, what happens? Okay, so let me do one thing. Let me then make a copy of this wall. So I'll give this, call this a copy, and then I'll edit that copy, and I'll just call this an uninsulated lightweight wall. So let me do that. Yeah, okay. And the easiest way for me to do that is to change this layer from insulation into an air gap. And that's quite typical when you're doing lightweight construction in many parts of the world. So to put an air gap, I will go to this one called gases and get an air gap. So if I put a 25 millimeter air gap, it'll put it there. It puts an R value, which you will find here, 0.18 R value in the air gap. And you can calculate the total U value over here, 1.3 something. But what we'll do is if we rerun this simulation, then you can see what the change is in terms of just changing the insulation on the wall. So 40% of the wall is solid construction, 60% is windows. So on the 40%, you've changed the insulation. And just because of that, we haven't changed any windows, either the size or the performance. We can just see what the difference is in energy. So that's one way of using Design Builder to test the construction. Now this will be, when you build your full model, it'll give you the impact on the full building. So what Mansi's done is taken one room and tested it. Now you can take beyond that. You can take not only the one room, you can take the building, and for the whole building, if you changed, what would be the impact of that? Why is that important? Because the building has got zones that are, what we call perimeter zones, which interact with the outside. And then there are zones that are sort of internal to the building. And then, therefore, those zones will not be affected very much by what's happening in the external walls. So you want to know what the combined impact is, so you get a realistic idea of what the savings might be. And that's what we're doing here now, okay? So in the same way that I did for walls, you can change the construction of the floor, change the construction of the roof. You have two kinds of roofs. So you can have a skillion roof, which means that the area just below the roof is air conditioned or conditioned. Here, simulation's complete here. Or you can have one where just you have a false ceiling and then you have an uninsulated attic type roof on the top. So here we go. Let me pull this out. So here's my new run, and you can see my timestamp has changed to 11:20. If I look at that in this case, and we look at the numbers now, so it has gone up marginally to increase slightly the energy use. And that's because if you look at the entire building, there isn't the majority of the area is actually in the big center zones that are over here. So if I pick one floor, you can see this area is possibly dominating what's going on in the whole building. Okay. Now, once you've done that, you may want to look at what's happening in the window performance types. Okay. So again, if we go and look at the windows, I'm going to leave the size of the window as it is. So we will leave it at 60% window to wall ratio. Each window is spaced at 2.4. The sill height is 0.8. But what I want to really do is to see what is the performance of this window, make a run, then change it and see how that affects it. Okay, so the run that we've got now has got this type of window on it. Okay, and if you look at this menu item here called glazing type, and if you examine what's there, that is where you can put the performance of the window. Okay. Now for windows, there are three main characteristics that you are interested in. The solar transmission is defined by this thing called the solar heat gain coefficient. In this case, this is a very good window, 0.24 solar heat gain coefficient. So it is only allowing 24% of the solar radiation, solar energy, into the building. It is actually rejecting about 76%. Okay. It's allowing about 40% of the light to come through. And the U value is an excellent 2.4 watts per meter squared degree K. So this is a really good DGU, double glazing. Okay. Now, this way of defining a window is called the simple window definition. You can do quite a complicated one. You can choose a series of material properties, select a whole bunch of products that are there, and you can certainly build it. And within Design Builder, there is something called the International Glazing Database. So you will find hundreds of products there. And there are a series of folders. You can pick up different kinds of glass from different manufacturers, and quite a lot of detailed data is available. But at early design stage, you may not need to do that. You may want to try and see where your numbers reach. Okay. So suppose you take a much more ordinary piece of glass. So you say you take something that has got a solar heat gain transmission of, say, 60%. Okay. And you also allow the light transmission to be much higher, to be about the same or a little bit more than that of the solar heat gain coefficient. And typically a single glaze window will be somewhere close to 6. So suppose I put about 5.6 watts per meter squared. Okay. And if so I should name that a different name so that we don't get confused. Here we are. I will change the name. So instead of high performance, I'll call it low performance. And the first number can be the solar heat gain coefficient, and the second number can be the U value. Okay, so I'm going to apply this one. And we already have the results from the first run, so I won't change that. Over here, this one. Now, let's see what happens if I put the lower performance window in there and test what the outcome is. So let me rerun this. And then we can go back and see whether there is an increase. I'm hoping there'll be a big increase in the cooling requirement because we are now letting so much more sun come in. There's a reasonably big amount of glass on the facade, so we should see some increased amount of cooling. And then I'll show you how to calculate the peak loads. Okay, so for looking at how the window performance can be altered, you can use this method. So you may want to go and talk to some glazing suppliers and find out what kind of performance numbers you can get. And by the way, when you use the simple window configuration, you can include the value, the performance of the frame in there as well. So when you give the U value, I've given it 5.6, that can include the performance of the frame. Okay. Now, metal frames, of course, are very highly conductive. They will bring down the performance of a good piece of glass. But if you're using either wooden frames or thermally broken metal frames or UPVC frames, then the thermal performance can be quite good. So you guys can go and check what's available. Okay. So let's see whether my hunch is correct. Now, once we've done that, I'll show you something on the shading part, and then we can go from there. Okay, we're almost there. Right, so loading that. Let me go and find my Energy Plus folder. Yeah, so the timestamp is now 11:28, which is what it is here. Open the HTML file. Let's see what the so here now you can see where the numbers were. I think they were about 74,000. Now the cooling energy number is 105,000 something or the other, right? So you can see that there's a big jump in the cooling energy that's required because the window is now much poorer in performance. Okay, so that's a way of looking at how the building envelope performs for heating energy. Now, I was going to show you how to look at peak cooling loads. So once you've set up the model and you've selected also, in this case, I'll leave it as Sydney, but you can certainly select New Delhi or whatever. There is this summer design weather data, and if you leave it at 0.4% with this multiple design months, and that's, I think, the default position. So for us, January, February, December are our hot months, and you can see here air temperatures are, the design temperatures are 35. In Delhi, it's probably close to 42 or something like that. There are wet bulb temperatures, which are the amount of humidity in the air. And then there is a range. So this is the minimum temperature. That's the maximum temperature. This is the minimum temperature. So it's going to go through the whole building and choose, do a calculation for the cooling load for every month, and then picks out the times that are where the building presents the maximum cooling load to the air conditioning system. So I'm going to test this for the whole year. So from January through to December, that'll capture all months. I am choosing the 21st day. The only reason I'm doing that is because the equinoxes and the solstices fall around the 21st of a month. I'm also not putting a design margin. So I just want to know exactly what the cooling load is, then if I want to oversize anything, I'll do that separately. So if I do that, and it's using the latest what's called an ASHRAE heat balance calculations for deriving cooling loads. If I run that, it will present a series of outputs for cooling load calculations. And you just need to be aware of a couple of things, and then you can easily do what you need to do for your sizing. So you can see it's running 1 day each month, okay? And it's running the 21st day with the solar radiation, etc. in the background. This is my plugin outcome. I don't need that. I'll go back to my design builder here. And in this case, I have to wait for the results to be loaded back into Energy Plus, because it generates a series of outputs that we will require to look at. So it'll take a few minutes. On big buildings, it'll take a while, but hopefully this is not too large a building, so it won't take too much time to generate these outputs. Good. So the outputs are here, right? So let me go to this summary tab, and there are a few things to look for. Okay, one is I've got the names of each zone. I've got the name of the block that the zone belongs to, and then it gives me what it calls design capacity. Okay. Now the design capacity is nothing but the total cooling load multiplied by any oversizing factor, which I might have put. Now I didn't put any oversizing factor, I put 1. So this number and this number are exactly the same, okay? And depending on what supply air temperature I've chosen, it will also give me what is the flow rate of air required, okay? Now this cooling load, for the chiller, it doesn't care. But if you are interested, then it breaks it up into sensible load and latent load. That's fine. The number we are looking for is this 11.87. Okay. There are a few things it tells you. This is what my thermostat was set to, so 23.9 degrees centigrade. This is the humidity in the room that it managed to control it to when it achieved this temperature. And that's the amount of cooling or the size of the cooling machine for that zone. And the time of cooling, maximum cooling, was January at 4:30. That will give you as much as you need. There's a lot more information that's here, and you can have a look at it. If you are an air conditioning engineer, then there are many other things you can look at. But for just doing building facade, this is sufficient. So for each zone, this is the number. If you add up these peak calculations, and I'll go for this total cooling load column, you can see that this building requires about 204 kilowatts. Okay. The only thing is, if you look at this time of maximum cooling, you will realize that each zone has a different time of peaking for cooling, right? So these zones are peaking at February at 2 o'clock, and there's some peaking in January at 3 o'clock, and there's some peaking in the morning at 10 o'clock in December. So they're all over the place. Each zone is peaking at a different time. So what time does the building present the maximum cooling load to an air conditioning system? You can learn that by changing this from non-coincident to coincident. So here you will see that this total cooling load has come down to 188. So if I go back, that's 204. If I change it here, it's 188. And the thing about this 188 is you will see that all of these zones are shown to have some peak at that time. Or what is the cooling load at that time? When you add it up, this is the size of the chiller that you might need. Okay. Now, of course, you might decide you don't want one chiller. You may decide that you want 3 different systems, 3 VRF systems, one for the ground floor, one for the first floor, one for the second floor. And you can adjust that. I won't teach you that this time, but I'll show you how you can do that. And that is, if you then start looking at it by system, you can actually size the condensers for each different floor separately. Okay. Now, as an architect, you don't need to do any of that. Push it back to building level. That's all you need to do. And you only need to look at this number to give you the peak cooling load for the building. For each individual zone, you can find out what is the peak cooling load over here. Okay. And by changing your windows and your shading and the size of your windows and the type of shading device, etc., you can play around and see how the building reacts. Okay. So let's go back here and let's start looking at some of the shading devices that you can put on windows and what sort of impacts that they might have. Okay. Now, you can see here that I've got one shading device here, okay, which I put for the entire ground floor, between the ground floor and the first floor. Okay. Now, what I'm going to do is I'm going to move that out of the way. I'm just going to put that on the floor so where it won't give me any shading. Okay. Instead, I'm going to start putting some shading devices on these buildings. Suppose I pick one of the floors, and this is just to show you how it works. So suppose I pick this middle block, and I say that on this middle block, I want to put some shading devices. So I've gone to this first floor block, and I open the openings tab. If I open up this thing called shading, and if I look at this local shading, in this local shading, I can put physical shading devices that are part of a window. Okay. So let me pick one of these to show you. I'm going to pick this one, and I'll just make a copy of this. And I'll just call it, I'm just going to call it general shading. Okay. And there's a reason for that. In this one, I can turn off or turn on louvers, turn on or turn off a side fin, turn on or turn off an overhang. And I can change any dimension I want. So this vertical offset, this projection, all of those things I can turn off here. So suppose I say I want a 60.6 meter projection on the overhang, and that I want on this side fin, I want just 30.3 meters, okay? And I only want one side fin on the right-hand side. And for the present, I won't put any louvers, but if I wanted to, I could turn louvers on as well. So by just typing some numbers, I can actually apply. Oops, I did that at the building level. I should not have done that. But anyway, that explains how it works. Let me go back, remove it. Just check, okay, it's all gone. Now I'll go to the first floor and I'll reapply it on the first floor. Okay, I've put general shading, correct. So now, so just that one floor has got those shading devices. Okay, you can see this gray here. If you want to see it more carefully, you can use the visualization tab, go to the render view, and you can see here. Okay, now you can now rerun your energy simulation with and without the shading devices, and you can see what impact it might have on energy and what impact it might have on peak cooling loads. Okay. Now, peak cooling loads are a little bit funny, and that is because depending on the orientation of that particular zone and whether there's any shading from any adjoining buildings, your shading device may or may not have much of an impact. Okay. But overall, if you apply it the way that you've learned by looking at Mansi's lecture just before this, that the south, the east, and the west are where you need to provide shading devices. So you can put shading devices on those zones. So you can basically just select those zones, put the openings tab, go to the openings tab, put on whatever shading devices you want. You can design the shading devices using the methods that Mansi showed you, and then you can study its impact on energy use on peak cooling loads by working through those with Design Builder. Okay, so that will give you quite a good sort of design process to test your building's performance. And once you've got the building facade optimized, then you can start thinking about air conditioning systems and so on and so forth. Let me also show you here. Let's say I'll go to the top floor. So the second floor, and put some louvers on so you can see what it looks like. I will put this one, that's a standard 0.5 everywhere, but I'll put it on so you can see what it looks like. Yeah, you can see that. So now we have two different kinds of shadings. And if I want to see it clearly, you can see how that sort of works. And the other thing is, of course, if you really want to see how it's affecting, you may be able to drop the take a section and actually have a look at what's going on during the day. So you can change your times and see what impact your shading device is having on different zones. Now you can see here that only the real wall is shown up on these rendered. All the false walls, the virtual partitions, which the air conditioning engineer can use for sizing, will remain without being seen. So it still looks like the open plan office here. You can go even lower and look at what's happening at each floor. So we can see how just the overhang, whether it has any impact on the penetration of the sun or not. So I had set it up as April, which is neither summer nor winter, and I was looking at the impact. But if I was looking at, say, in Australia, we'd probably be looking at December as a summer month, and then you can kind of see what's happening. So suppose I say noon, you can see that there's almost no sun coming through because of the way the latitude is. Now, 32 degrees south latitude is very close to what Delhi's 32 degrees north latitude. So it's on the other side of the equator, but it's similar. So, those are things that you can test quite easily by doing this. And of course, you don't have to put it for the whole zone. You can go to just one of the zones, and you can go just to one wall and put it there, and then all the windows on that one wall will get the shading device. You can go to an individual window and apply the shading device as well. So there's quite a lot of flexibility available within Design Builder to check those things. Now, one other thing that is quite useful to know is that in the openings tab, I showed you the local shading, but there's also something here called window shading. And in this window shading, you can actually start using blinds. Okay. Now you won't be able to see blinds in the geometry or the visualization, but the blinds can be positioned either inside or outside the window, or if your window is got 2 panes of glass and there's a big enough gap, you can put the blinds in between the glazing as well. Then once you've done that, so let's suppose you put some blinds on the outside, okay? Then you can decide how you want to control when those blinds are brought down or taken up. You can either put a schedule and say, okay, let it come down in the summer months, or you have a number of control strategies that are already built into Energy Plus and Design Builder. So for example, you might say you want to control it by outside air temperature. So if you say that whenever the outside air temperature goes beyond a certain temperature, say 30 degrees, you might say as soon as the temperature outside exceeds 30 degrees, pull the blinds down. So it will do that, okay? You can provide schedules. So you can set your own schedule and you can tell it when it needs to work. So there's quite a few options available for you to do that. Read the manual and you can work on that. So that'll give you other options that you may not be able to see on the geometry part, but if you look at the results, you will be able to see how the results work. Now, this one, you've got to be a little bit careful because some blinds don't, all blinds don't work with all the control strategies. So if you start to get some strange results, then you may need to go back and read the manual and pick out what's going on. But the simple schedule works very well. We've done some very interesting analysis on that. And if you've looked at the first link that I gave you guys and you were there for the first webinar, you would have seen that we looked at the external blinds for a west-facing window, and we showed what the mean radiant temperature change was because of blinds. So that you can do from here. Okay. I'm looking at the time. We're about within 10 minutes, so we might leave that for questions. And if there are any questions, you can put them on chat, and yes, Meena will control that. Thank you.
Thanks, PC. We have been getting a few questions, and I also noticed Mansi has been answering to a few of them. But one question that has come in, which is very design builder specific, is if you could talk a little bit about the input parameters required to conduct energy performance tests for building envelope. I'm sure you cannot list all right now, but if you could talk a little bit about that.
Yeah. If you watch the video link on, there was an introduction to energy simulation. That one actually covers all those inputs in some detail. Okay. So when you are, before you run a simulation, you need to tell the energy simulation many things about the building. You are already drawing the building, so you're telling it something about how the building's floor plate is, how you've divided it up into zones. Then in each zone, you are saying, okay, what is the construction material and the windows? So then you're talking about the heat transfer, the building loads, as it's called. And there's quite a clear explanation in that lecture that I've given for all of those things. Then you are telling it, okay, what is the peak design occupancy for each zone? How many people will there be in a zone if it was fully occupied? What is your design condition for that? And then you're saying, okay, how does the occupancy vary during the day? How does the lighting system vary during the day? How does the equipment get used during the day? So it needs to know all those things. And then you need to tell it, okay, what is the thermostat temperature you're aiming for? What temperature do you want to maintain in the zone, right? And then it needs all that information before it can actually do a calculation. If you don't have those informations correctly specified, then the results you're going to get are not going to be reliable. But once you've set all those various parameters, then that'll start to give you some good outcomes. So you might say, well, how do we get these numbers? Okay, and my suggestion would be that something like the ECBC, the Energy Conservation Building Code, will give you, for India, it will give you some good schedules for occupancy, lighting, equipment, those kinds of things. And then typical air conditioning design engineers will tell you how much fresh air they bring into the building, those kind of things you'll get from them. Glazing suppliers can tell you what kind of glazing is popular on, high performance commercial buildings. What are those three values I showed you? U value, solar heat gain coefficient, visible daylight transmission. Those are the things you need to understand. And then U values, R values, all of that, you can start from the ECBC requirements and then improve on them or change them. And then shading might help, those kind of things that Mansi was talking about. All those things would help to improve your design. I hope that answers the question.
Yeah, sure. Thanks, PC. One question we got about the division that one of the teams is participating in. So the question is, my team has the typology as construction worker housing, and their project partner site only has male construction workers living and working there. So there's no family of female construction workers. So should design solution cater to only the male population, or should we also provide provision of family style units? So the answer to this would be that you would definitely have to provide a narrative to why there is no male or family construction workers, involved or, a part of the project. But because this is not a very typical situation, and the jury would want some narrative or some justification on that. And if you have any further questions about it, you can write to Uday, and we'll respond with a response based on the question that you sent in. Also, there were a few questions regarding how to decide the angle of shading devices, or what is U value, and what is the unit of irradiance. Those kind of questions, which I I mean, I see Mansi has responded to those, but I think it will also be helpful if all of you start looking at the self-learning modules. All these questions have been answered in those videos, and I think it will be helpful before you begin to start using Design Builder to actually look at these videos and understand the basic concepts of building science. So that would be extremely important in this case. We do not have more questions, PC, but I have one question, if that's all right, which is, if there are any tips that you would like to give our students, they're going to begin with their Design Builder modeling from this in this stage, and if there is anything that they should watch out for, the kind of mistakes that one is likely to make, if you have something to say on that.
Yeah, I think that's a very good question. Thank you for that. There's a PDF that I gave you on, my first model. I think if the students can follow that carefully, some of those common mistakes, I have tried to give you a process which hopefully will avoid some of them. But, then it sort of gives you a way of, okay, first draw this, think about this, put this information in, that kind of sequence, which I think is quite, when you're doing your first model, I've learned from 15 years of teaching students that these are common questions and things. So I've tried to put a little process down. So follow that for your first model at least. And then as you get better and more expert, you can certainly deviate from that.
Right. So this PDF that PC is talking about is available under the learning management system. If you go to the webinars topic, there are the links to the recordings as well as these additional resources that PC has provided. So you can take a look at the PDF as well as earlier the recording that PC was talking about. Both of them are available over there. And I think that's all from this session today. Thank you so much, PC, and thank you, Mansi, for your insights on building envelope and shading. I think it was extremely helpful for students to look at the way you have looked at your projects. And we will all see you in next couple of weeks. There is a CFT related webinar that we are planning. You will get the details soon about that as well. And yeah, that's all. Thank you. Thanks, PC.
Thank you. Thanks, Mansi. Thanks, Yashima.
Thank you, PC. Thank you, Yashima. Thank you, everyone.
Bye.